I'd like to start thanking the organizers for this great invitation, and I'm very happy to be today here with you. So I want to talk to you about neuroscience and artificial intelligence, which are my main research lines. I'm trying to connect these two disciplines and try to find common points that make neuroscience understand the brain in a better manner and to improve the algorithms of artificial intelligence. And thank you for the presentation. I will just summarize. I'm a faculty member of a Chilean university, it's Universidad Técnica Federico Santa Maria in Valparaíso, Chile. If you don't know this university, this is a great, incredible place. We have undergraduate, and graduate programs mainly focused on science and technology. I'm also part of a research center, which is called the Advanced Center in Electrical and Electronic Engineering, who's trying to push forward the development of electrical and engineering technology. And I recently joined, this is also a new center in Chile, which is called National Center for Artificial Intelligence. We launched an artificial intelligence plan during the last year. So this is part of this initiative trying to push forward the development of artificial intelligence in Chile. Okay, so after this introduction, today we're here to talk about neuroscience and artificial intelligence. And when we think about neuroscience, the first thing that comes into mind is our brain. Yeah. Inside our brain, we have neurons that have inspired the development of artificial intelligence since the 50s. We have neural circuits, which are physically branched, and there is also plastic, and the neural circuits are being shaped according to what we do, what we think, what we act. And everything that's happening inside the brain is the main reason why humans act like humans. Okay. The good thing about this is that during the last 10 years, it has been a huge effort around the world trying to understand what's happening inside the brain. So this is a Twitter of International Brain Research Organization, the IBRO, who is celebrating the creation of the International Brain Initiative. Around the world, there has been several brain initiatives. We have here in the United States, the brain initiative launched by President Obama in the last 8 years, approximately. We have the Human Brain Project in the European Community. We have the Canadian Brain Research Strategy, Australian, Korea, China, and all these projects around the world have been trying to main focus on understand how the brain is working, trying to understand how the neurodegenerative disease appears, try to understand how we are doing computations and how we are representing the world. The thing is that not only neuroscience has advanced a lot, but also artificial intelligence in the last 10 years. So the good question is, how can we combine these two disciplines? How can we use artificial intelligence to better understand neural processing in our brains? And how can we use the understanding of the neural circuits in our brain to develop better artificial intelligent algorithms? Okay, so I want to give you some insights about this. I want to talk about some of our works and some works that are not of us, but are inspiring this crossing between neuroscience and artificial intelligence. So the first thing is that the brain, even if the brain is responsible of what we are, the brain is not isolated. The brain lies inside our bodies, okay? And everything we do, everything that's happening in the brain and cognition is the result of the interaction between this brain and our bodies, and also our experience with the external world, okay? So the brain is not an isolated neural machine computation, but everything it does is immersed and is shaped by our bodies and our interactions with the external world. So these, of course, are not new ideas. These ideas have been highly pushed by Gibson in the ecological approach of visual perception, or by Francisco Varela in the bodied mind, and how effectively all the computations inside the brain are dependent on who we are, which are the actions we need to perform to survive in this world, and of course the shape of our bodies. So we can briefly summarize this idea in these two sentences. The first one is that mental states are determined by different factors, including sensory structures and interactions with the environment. And the second is that actions form perception. That is, the ability to perceive is built up through many previous experiences, actions, and abilities. So we cannot dissociate the brain from the body. We cannot dissociate the brain from the experience. So within these frameworks is with actually robotics emerged as an interesting platform to test all this idea and to test how the neural circuits, how the computations, artificial computations are shaped by the robotics bodies, but what robotic can do or not, and depending on the task, which are the best algorithms that emerge from this interaction. So I want to give you two examples about this idea. The first one is about gait learning in leg robots, which challenges task in the world of robotics and artificial intelligence. So the big thing is here, the question is, how can we make a leg robot to walk? So the classical manner to do that is to implement what we call a kinematic model of this robot, in the sense that all the shape of the robot is included in this kinematic model. And doing matrix transformations, we can exactly know what to do with each part of the robot to move, for instance, one leg from one place to another. But what if we consider a completely different approach to make this robot walk? We don't tell them anything about its shape. We only tell the algorithm how many degrees of freedom the robot has. So it means how many motors. In this case, it's 9 motors. And the robot starts to explore itself. Explore itself in environment. And according to an exploration, are we seeing the video? No. So the robot starts to explore itself. So we build a neural network, that the neural network is not only learning the connection weights, but it's also learning the architecture of the neural network. So the robot starts to do movements, trying to explore itself and trying to find a better manner to reach the goal. And the goal in this case is move from one place to another. Okay, this is an error. We did a mistake with the algorithm, and we put more force in one of the legs, and that's the way the gait was learned. Okay, so to do that, we use neuroevolution algorithms for learning gaits in leg robots. We try different, this is a neuroevolution, this is a neural network that it's not only learning the connection weights, but it's also learning its shape. We use an algorithm that's called IPRNet. We used another one called TOE-IPRNet. We included time delays between the connections. We also shaped different morphologies of this neural networks. We tested in 2 different robotic platforms. We have the one on the left with 9 degrees of freedom, the one on the right with 12 degrees of freedom. And this is the final walks gaits that emerged from this learning. This was for the 9 one. And this is for Argo with 12 degrees of freedom. That's a bit scary, I think, because it looks very similar to what we observe in nature. So following this line, we have this new robotic platform. This is the Icap. The Icap is it's like a 3 or 4 years old, the size of the 3 or 4 years old child. It's an incredible platform coming from Italy, from Italian Institute of Technology. There are 42 Icaps around the world. This is the first one in South America. So this platform contains auditory system, biaural auditory system. It has stereo vision. He has touch sensor all around the body. He knows exactly where you're touching it. In the hands, he had more than 100 sensory points to detect and grab anything. So definitely this platform will help us to understand a lot how the learning is conditioned to the shape of the body, and also dependent on context and the interaction with your environment. Okay. The second example I want to talk to you, it's about vision and perception. Okay. how the study of vision could help us to develop artificial intelligent algorithms. And specifically, my research concerns the study of the retina. I don't know if you're familiar with the retina, but the retina is it's a layer of cells located at the back of the eye, where the light crosses all the retina up to the photoreceptors, which are doing the transduction between light and electricity. And there are many other cells. So after the photoreceptors, we have horizontal cells, bipolar cells, amacrine cells, and finally the green ones, the little green ones here, are the retinal ganglion cells, which are gathering all this electrical activity and generating the action potential, the spikes that are traveling through the optic nerve up to the thalamus and the visual cortex. So study the retina is a study a real neural network that could give us a lot of insights how biology has solved many information, treatment, processing, and incredibly how the evolution also has answered the way we are perceiving the world. So if we're doing a schematic here of how many cells, it's an example from a rodent. We have 3 types of photoreceptors. We learned at school that we have cones and rods, and cones in humans, we have 3 different types. And in rodents, we have 2 types of cones and 1 type of rods. We have some horizontal cells, a variety of bipolar cells, a lot of amacrine cells, and much more ganglion cells. So if we think that each of these neurons is connected to one of all the others, what we got as a result that the retina is not only doing the transaction between light to action potentials, but it's computing hundreds of parallel processing of the visual external world. So this is more or less the type of connections that we have between this type of neurons. So the black dots are excitatory connections, the chemical as excitatory connection. The white dots are inhibitory connections. And we have the ones that looks like resistors that are, in fact, that are produced when the axon of one neuron is touching the axon of the other neurons. So it's a very complex real neural network. It's very interesting to study. So in Chile, we collaborate with the Centro Interdisciplinario de Neurociencia in Valparaíso, specifically with Dr. Adrian Palacios, and we study the retina of this Chilean endemic rodent. It's called the Octodondegus. The interesting thing about this rodent is that it's a diurnal rodent. It's not a night rodent. So its visual system, it's very similar to what a mammalian or visual system looks like. To study what's happening in the retina, we have a system of 252 electrodes. So we are able to dissect pieces of the retina, mount the retina on this microelectrode array. We recently acquired another system with 4,000 electrodes. We can stimulate the retina with real images, and we can record the electrical activity generated by the retinal ganglion cells, which are the last layer with this information that comes out from the retina up to the visual cortex. So as a good engineer, what we do to understand what's happening inside the retina, we consider it as a black box, okay? And we apply as input visual white noise. And we record the response generated by these retinal ganglion cells. And from a single piece of retina, we can recover like between 200 or 300 neurons. And we can broadly find 2 families of neurons. The first one are the off cells. The off cells are cells selective to a small patch inside our visual field, and the cell reacts when the light turns off. That's why it's called the off cell. And we also find another family of cells, which are the on cells, that is the other way around. They're very happy when the light turns on. So if we can do this study, push further, we can see that the properties of these cells are changing depending on which place of the retina you are located. In the central retina, we have smaller cells that are very slow. In the peripheral retina, we have broader receptive fields with cells that are reacting very fast. That's why when we read something, we are facing that on the central retina, but in the surroundings, we are seeing things that are moving so fast, but we don't have the spatial resolution to understand what's going on there. So this is a very simple exercise to consider these cells as linear filters, and we are convolving the input video, which is the video on the top, with one cell from the center and one cell from the periphery, just to show you the different types of information that these cells are extracting. Okay, so in the retina, we are not only finding this type of behaviors. We are also able to find cells that are reacting to the motion direction of the input stimulus. So it says that we apply these drifting gratings at different frequencies and different speed, and we will try it at different directions, and we can see that our cells, that they don't care that much about the direction of the stimulus, but there is another ones that are very selective to the motion direction, which are the motion direction selected cells, and there is another ones that are very selective to the orientation of this stimuli. And this is very striking finding in the sense that these properties were always thought to be only part of the visual cortex and never be part of the retina. Okay, and also if we present stimulus that are considering statistics of what the visual field looks like for different animals, in this case the rodent, we can observe that cells sensitive to speed also are emerging. So you're not only measuring motion direction, but also you're sensitive to speed of the stimulus, and that's also happening at the retina level. And this is another behavior, is that all these properties of the retina, they're also depending on the light conditional level. If we are in the daylight, the retina behaves on one manner. If we are in the night, the retina behaves a completely different manner. So this is an example. ND2 is a lot of light. ND5, it's very dark. And this is an image showing the receptive field of a neuron. And we can see that this is an off cell. Do you see the mouse? This is an off cell located in this part of the visual field. And as soon as the light goes down, it switches from cone to rods. And what we observe that the receptive fields are bigger and it's shifted inside the visual field. So this property is found in many other sensory systems and many other information processing algorithms. When you are in face of a very noisy environment, you have to increase the size of your receptive field as much as you can. And this is another cell that is not only shifting the receptive field or increasing the size, but it's also shifting the polarity. So a cell that's supposed to be reacting to when the light turns off, it becomes to a cell that's reacting when the light turns on. So the study of all these different properties, of course, how the biology has solved the problem to maximize the information processed by our brains when we are in day-night, with a lot of light, or we are at night. Of course, it's an interesting issue to inspire the development of artificial intelligent algorithms. So we have done this is about our lab, about our research, trying to understand the retina. So the question that arises then is, how can we use this marvelous encoding mechanism to process image or videos? Okay. I brought also some examples. This work was performed by Barco and Pierre Corprops at INRIA in France. Is that the retina is also doing a lot, it has an internal gain contrast mechanism. So it's equalizing the contrast of the image in a very wise manner. So we model this equalization and we applied it to images, and we are able to deal with images and video with high video contrast. This is a tone mapping problem. And also we can apply some of the things we have learned about the retina in a robot navigation in complex environment problem. So what we have here, this is a deep reinforcement learning architecture with two convolutional layers of cells. The first convolutional layer, what we did is to replace it by the two cells found in the rodent's retina. So the task here is an artificial agent moving. Is it working? Yeah. moving inside a maze. It has to collect some reward, and how is a reinforcement learning problem? It has to maximize the collected reward within a given time. So what we did was the first convolutional layer here is in charge of extracting visual features, the visual features needed to maximize the reward. And what we did was to replace this first convolutional layer by the linear model of two cells found in the rodent's retina. One cell placed at the central retina and another one from the peripheral retina. And what we observed, so we ran the same test, and what we observed in the static maze, for instance, that the algorithm not only can collect similar rewards as the previous architecture, but only that the collection of this reward has speed up a lot using the visual sensor inspired by the retina. So in the case of the random maze, this behavior is not that clear in the sense that they're very complex tasks and many other things must be included as well. So what about other brain structures? So I've shown you some examples about the retina, but what about other brain structures? And this is an example coming from the literature. It's not coming from our labs, that it talks about the entorhinal cortex. The entorhinal cortex is an area in the brain that it's mainly focus and memory processing and space localization and time perception, and encode the time perception. And this small area, it's also the interface between the hippocampus and neocortex. So what neuroscience tells us about this is that in this region, we can find things that is called grid cells, place cells, and head cells. So grid cells are the result like kind of a spatial map of where we're moving inside an environment. And this grid cells is reacting, sending spikes every time you're moving at certain points inside the space map. We have the place cells that are highly reacting when you are located at a specific time of this space, and we have the head cells that are encoding the position of your head given a specific location in the spatial map. The good thing, this is literature in neuroscience. These guys got the Nobel Prize for the discovery. And the thing is that we can use this knowledge. In fact, we cannot use this knowledge. There's researchers implement an artificial neural network for the navigation task. And what they found, when you look deep in this neural network, and when you observe what this neural network has learned, you can see that most of the receptive fields of this neuron are very similar of what are the grid cells, plate cells, and head cells are found in the literature. And moreover, they applied all this learning. So they selected which kind of neurons are similar to place cells, head cells, and which are not. And they ran this navigation problem algorithm. And this, in green light, we have the state of the art. And in the state of the art, if we add the place cells, the reward collected increases. And if we add the grid cells, the total reward and increasing even more. So as a conclusion of this work, we can see that use deep reinforcement learning, this space representation shows to be very effective for a visual agent to locate targets in challenging, unknown, and changing environments. So the cross between neuroscience and artificial intelligence is something that's calling the attention around the world. In NeurIPS in 2019, there was a workshop called Shared Visual Representation in Human and Machine Learning. In the same NeurIPS version, we had another workshop that's called Real Neurons and Hidden Units. And Bernstein Neuroscience Conference in Germany that is happening every year, this is 2020, there was a satellite workshop also called Neuroscience and Artificial Intelligence. In Uruguay, we had the virtual summer school talking about neuroscience and AI for all, and they have a specific focus on the cerebellum and how the cerebellum is shaping a lot of our behavior and can we learn from cerebellum. And we are in Chile organizing this Latin American Computational Neuroscience Summer School every year. this, so not every year, every 2 or 3 years. This is the 5th version of the Latin American summer school that we organized in Valparaiso for this January. So this is the Chilean summer school. Is the North Hemisphere is winter, and this we choose in every version as a specific focus, and the focus for this summer is machine learning and artificial intelligence. So you will see the call for application will open soon. We really hope to have all the fundings to make this summer school possible, and I'll let you know to all the community, and we will be happy to receive you at Valparaiso this summer. Okay, with that, I wanted to finish, so thank you very much for your attention. This is all the people that is making this work possible. This is the funding, and so thank you very much. I'm happy to answer any question. Thank you.
Thank you, MariaJose. Let's see, we have questions. We have questions in person. Virtual? Oh, we have a question. Yes, please, so everyone can listen. What was your question?
Hi, thanks for your presentation. I was wondering if you have any insights or maybe opinions on why do we put a lot of effort on vision when we have like probably a larger organ like the skin with more receptive fields. So why don't we put also that effort on that?
Yeah, I work in the Retina because it's the equipment that we have, it's the collaboration that we have, I think the interest we have. And study other parts of the body, other parts of the neural system, it's not that easy in the sense that you have to, if you want to study them, you have to dissect those tissues and measure the electrical activity produced in a very controlled environments and controlled conditions. And that's not that easy. And vision, in fact, is one of the sensory systems. And what we have learned in neuroscience, that the principles ruling the sensory system are very similar to each other. So the things that we are able to learn in visual system are also present in some somatosensory systems or any other system we have.
Okay, thanks.
We have another question here.
Hi, Maria. It was a pleasure to hear you, and it saves me a lot of time afterwards. But yeah, I want to know what do you find really exciting and the top neurological or neuroscientific finding that inspire you the most, and based on your answer, what would be the future of your research? Because it sounds exciting, and of course, it's going to be very interesting to follow up.
Yeah, it's very exciting in the sense that if we are able to understand which are the principles underlying sensory system or neural process, etc., we are answering how the biology has solved by evolution many aspects to maximize the information, minimizing, for instance, the metabolism energy. Okay, so what are the insights about that? What is the next? Of course, we have to use, as I showed at the beginning, neuroscience, what we learn in neuroscience can inspire the development of artificial intelligence algorithms in the sense of information processing. For instance, the retina, in humans, we have 300 million of photoreceptors, and we have only 1 million of ganglion cells coming out. So the information is being compressed a lot. So the autoencoders, for instance, are very useful tool to understand what's happening inside the retina and maybe to improve or to rethink the way we are considering autoencoders for many other visual tasks. And so and the other way around, the artificial intelligence could help us a lot to understand how the brain is doing computations. What are the best stimulus? How can we interpret, the graph neural networks, the retina? The cells are not independent encoders. In many reasons, in many scenarios, there is a population coding. So there are patterns that's called neural ensembles that are reacting to different tasks. And these neural ensembles are present in motor cortex and many other parts of the brain. So graph neural networks are now a very striking opportunity to understand how the retina is encoding a visual sense. Yeah.
Thanks for your talk. I wonder about the the study that you showed, in which you replaced the first layer of the network with a.
Sure, but can you repeat, please? Or
Sorry?
can you repeat, please?
The work that you showed about the replacement of the first layer of the network with the model from the neuron. Do you think this will lead to a better to the model to generalize better? Do you think this is because usually the first layer of the network, independently of the data set you train, usually it's similar. Those filters are similar with respect to each other. So I wonder if when you study such models, neural models, and you replace them in the network, would this lead to a better generalization of such models?
What we have done, for instance, is to create an artificial neural network to emulate the retinal response. That's something I didn't include in this presentation. And so we train the network with the white noise, the same white noise that we collected, the neural response of the retina. And then we applied a completely different white noise input, and we are able to recover the same properties, statistical properties of the network. And to do that, we are preserving all the cell layers, and we can check that specifically the receptive fields are a generalized version of the virtual stimulus, and it's not very dependent of the statistic of what we're showing.
Thank you.
Any other question? Do we have a virtual question? Oh.
The talk was great. As you know, we are all social peoples. We make a lot of emotional decisions. So when you use the example of the retina or specific organs in the brain, but what about the our thinking and perspective are different from social perspective and individual perspective. So in the future, is there any work where we see the group of autonomous agents or like a society where they can think differently, not as an individual? Is there any work in those directions?
Like a swarm robotics or things like that, no?
Yeah, something.
The collective behaviors about.
The collective behavior.
In psychology, there are various studies about collective behavior and how our behavior depends on what the other agent is doing or things like that. And there are some works about that. We did it like a few years ago. We did some work about a model that were 3 agents, and the agents were able to perceive a kind of mood of the other agents and how the collective behavior was biased depending of that mood. And that was inspiring a psychology research. So there are some things we have to look around that. Of course, there are people studying how the collective behavior is shaped by different aspects.
Okay, thank you.
More questions? I have one question. So great talk, amazing talk about it. Clearly in AI, we are talking about deep learning networks, where the deeper the network, the better. However, you're proposing evolutionary algorithm, you're proposing maybe reinforcement learning. There is this need when we go to deep learning that we need more power, more resources. We're talking about megahertz of watts of energy to make these models, these deep neural network models to work. When we think about biology, we think about the brain, and the brain only needs 30 watts or so, which is very, very low energy. So it's very efficient in that sense. They don't need that much energy. What are your thoughts in terms of evolving AI? In which direction we should be evolving in the way that we can be more efficient with the energy consumption?
Yeah, I think one of the big difference between artificial computations and the brain is the hardware, in the sense that the brain is a very asynchronous machine. So it's not reacting all the time. And in hardware, we have the von Neumann architectures, which are constantly producing running the algorithms, and to emulate the asynchronous behavior, it's pretty hard. So I think the direction, it's not only software, it's also hardware to move forward neuromorphic computations. So neuromorphic architectures, which are being pushed by Meta, Google, and many companies around, I think it's the way we have to move in order to make our algorithms more efficient.
Thank you. Do we have more questions? If not, please join me in thanking MariaJose for the amazing talk.
Thank you.